Hello everyone, this is Metrum Institute 205, the web version of that course. We're working on Chapter 9 today, Advanced Function Writing. And I am monitoring my question box in case you have issues either with the technology or with the material that we're discussing. Please feel free to post a message to me there. And unless I hear otherwise, I'll assume that you have video on your screen and can hear me, good audio. Maybe I'll just post a quick chat to that effect in case you don't have audio. We spoke about functions earlier in this course, Chapter 4, and when we did so, we concerned ourselves mostly with the externals of function writing, namely arguments and calling functions and so forth. Today we're looking at the internals of function writing. It's really a very exciting topic to me. Functions give a lot of power to your R code and to the process of developing scripts or packages or complex projects. You'll gain quite a bit of return from investing some effort in understanding how to write functions and how to write them well. When we look at function writing of any complexity, an immediate problem that we confront is how to detect or remove errors from functions. Even modestly constructed functions can have subtle errors that are not immediately obvious. We need tools for discovering those, or rather for correcting those when they do occur. We're going to try to write some functions today that create errors just so that we have a chance to debug them. And I see a question, has this R script been posted? No, it has not. Good question. I can post this later. What it is an excerpt from the book chapter. And the revised book with Chapter 9 has been posted. So all the code you see on screen is in Chapter 9 of the posted version of the book. And as I said, I can put this up later in case I make some modifications that you want to explore on your own. Now, you're probably familiar with the idea that functions can call functions, and those functions can call still other functions, and that's a wonderful tool of abstraction whereby the function that you call doesn't necessarily have to know or care about the details of the other functions, which means that you have to think less about what's going on down below. Okay, however, all that indirection could lead to issues when it comes time to understand an error. To illustrate, we're going to define a stack of functions today that calculate root mean squared error. I'm calling it root mean squared deviation on screen here, just so that we don't confuse the statistical concept of error with the coding or the syntactic concept of error that we find in the R language. So, and you probably will notice a typo in the book. My section 9.1 in the book still has this function defined the old way where deviation is actually defined as error. I changed that recently but forgot to change it systematically. I'll fix that later and repost the book. Oops. I want to source this line of code and that's not working for me. How do I get that? I did not mean to do that. Deviation, okay. That worked better. So we define a function called deviation, which does what you'd expect if you take, say, a vector of 10 numbers. It calculates the difference from the mean. Fairly straightforward. We're also defining a function called squared, which does pretty much what you'd expect. We won't demonstrate that. And we also have a function called root, simply power to the half. And we're going to hard code some values right now and display those. Those are going to be our test values. And then we put them all together in this string of functions that burrows down into the stack here. I love writing these. Actually, it's more of a stunt than anything else. It can actually make your code very hard to read if you do a lot of this sort of thing. But in this particular case, it works nicely. You see that we're calculating a deviation of these values, then we're squaring that deviation, taking the mean of that, and then finding the root for root mean squared error, analogous to the traditional statistical concept. So let's go ahead and run that line of code. And suddenly we see a bunch of mess on the screen, as we had hoped. There is an error in x minus mean. There's a non-numeric argument to a binary operator. Also a warning message about something not numeric or logical returning NA. Okay, all kinds of mess. In an ideal world, our function would have worked on the first try and we would have just gone on with our script or our assembly or our project, whatever it was. Now we've got to deal with an error. Well, I could have shown you an error just in a single function. That would have been a little less interesting. Right now we have an error occurring in one of these functions, all of which were called either directly or indirectly. And to understand where the error occurred, the easiest thing to do in R is to call the function traceback. Traceback looks at the stack of functions and shows you the trail, as it were, of functions that were in operation when the error occurred. There are other debugging mechanisms in R that I discuss in the book chapter. Please read the book chapter for a formal review of those. Here we're just going to call traceback and say, okay, here's what's going on. First we called root, yes, knew that. Root called mean called squared, squared called deviation, and deviation is the function in which the error occurred. So we say to ourselves, okay, fine. Then we can go ahead and debug deviation, try it again, and have a chance to examine in excruciating detail exactly what's going on at the time of error. Now, you're familiar with the concept of debugging, perhaps from other exposure to computer languages. In R, we have a very simple mechanism for debugging, and of course there are more sophisticated ones. I still use this one almost exclusively. It's called debug. Here we just name the function of interest, the one that's causing the problem, and you don't even have to quote it. You just say debug deviation. Then I'll do up arrow in my interface to recall the actual line of code that gave the error. And this time, oh, that took longer than expected, probably because we're working over a slow internet connection. This time what happens is that the function call does not go to completion. What happens is root calls mean calls squared, squared calls deviation, and deviation pauses. The function opens, and I get a prompt. Instead of the function completing, I get to sit here inside the function and execute it one line of code at a time until I figure out what's going on. Not only do I get to execute the function one line of code at a time, I also get to type my own expressions to test the values of various variables that may be here and available and may have some sort of problem. So when I'm in debug mode and I've got my problematic function open like this, the first thing I do, I always type ls parens to show what objects are hanging around. And here I see, well, there's nothing here but an x. So I'll type x on the command line, and I see the values of x, and those are, well, I was going to say they're exactly like I've defined them, but they're not really, are they? Because I define them as numerics, and here they look like character. They're all quoted. That's actually a clue. What actually is going on here is that NA here is in quotes, which is a character string. And since all the values in a vector have to have the same type, R has automatically converted all these other values to character as well. And that's going to be part of the issue here. So I say, okay, let's leave that as it is, and we're going to go ahead and execute the next line of code. And it says x minus mean of x. Well, to do that, all I need to do is hit the return key, and this line of code will execute. Actually, I don't want to do that right away because I know that it's going to fail. I want to understand why it's failing. So instead of hitting the return key, I'm just going to wait here and think about it in a little more detail. Why don't I just try a piece of that code? I could try mean of x. And well, actually that wasn't an error, but it did give a warning. It says argument not numeric or logical, returning NA. So yeah, I see the NA that was returned there. Here's an interesting property of the function mean. If you're taking the mean of text, it doesn't give you an error, it gives you a warning. That's very interesting. So now I have this NA, which is actually a numeric NA, and I'm trying to subtract it from a character vector. Well, let me try that on my own here. Without typing the return key, I'll just say x minus mean x, and waiting for the internet. I see the error that I saw before. It turns out that it makes no sense to subtract something from a character vector. That's what's causing the error, because the subtraction operator here is a binary operator and expects to have the same type on both sides, not character on one side and numeric on the other side. Even if it were character on both sides, you still can't do that because the subtraction is not defined for characters. So what we need to do here is get out of this. What I'm going to do now is finally actually type a return stroke, which will give me a give me the regular error in regular sequence, and will also return me back to the command prompt. So I'm going to go ahead and give me one second while I turn off some stuff that I'm not using here. Okay, I'm using that. Great. I'm going to redefine deviation in such a way that it tests for the class of x. Okay, and that's done already right here in example 9.9. We found out what the problem is. The problem is that we had a non-numeric value for x. So we're going to define deviation this way. And when you redefine a function in R, if it was being debugged previously, now it's not being debugged anymore. That automatically turns off debugging. If you know what your issue is and you want to turn off debugging, you can simply say something like undebug. And probably this gives a warning. It says argument was not being debugged anyway. Okay, fine. So now we could debug deviation, or we could just try it the way it is. All right, we're going to do the same call before, root mean squared deviation of values, which have not changed. But now we're using a new function definition. And what this function definition says is, let's take x and see if it's numeric. If it's not, we're just going to return null and go on our merry way. If it is numeric, we'll go ahead and do the usual thing, subtracting the mean from the values. Okay, run the line of code. And I get back NaN, which means not a number. That's fine. No errors, no warnings, just not a number. Because I'm not sure exactly why that is. We know that values was not numeric. It says return null. Now I'm interested in exactly why that happened. And maybe it's not a big deal, but I'm going to debug deviation again just to make sure I understand it. Okay, now deviation is being debugged. I'll run that line of code again. And instead of running to completion, I open this little window, as it were, with a command prompt, and I can see whether or not x is numeric, for instance. Let's do ls again. Nothing here but a single variable called x, and I'll ask myself, is numeric x? It says false. So I would expect that this function will return null. I'll go ahead and hit return so the function actually executes. Oh, what I should clarify this. What happens is if you have a long function, then the debug process will step through at one line of code at a time. But it will always show you the line of code that it is about to execute. So you can decide if you really want to execute that line of code or not. When you hit return, the last line you saw is going to be executed. So here we're going to execute the if not numeric return null. Well, what we did right there was we stepped into the condition, we found out that we were not numeric, and so now we're operating inside the condition, we're about to return null. And now we're exiting from deviation values. Aha, now I understand what happened. Deviation function really did return a null, but it returned it to the function squared, and squared returned something to the function mean, which returned something to the function root, and the result of that chain of operations gives something that is not a number. Well, that's okay, we're not worried about that. Probably when you take the root of something that's null, you don't get a number. We know that there are other problems going on that we can fix ourselves. I suppose the thing to do in this case would be to define a new set of values where we write what we probably had originally intended. 1, 2, and then a numeric NA, then 3, 4, 5, like that. We could try root, mean, squared, deviation of the new values. And I misspelled that. My apologies. Deviation. Oh, we're still debugging this. Well, we don't want to debug this forever. We were hoping it would work this time. So what I'm going to do is break out of debugging. Good skill to know. I'm going to type the capital letter Q, not the lowercase q. That's how you quit R with parentheses. Just a single capital Q that gets you out of debugging. Now I'm going to say undebug deviation. Now I'm hoping that I understood my error and I can re-execute my line of code with the new vals and get an expected result. And well, I didn't get an error. This is good. But I didn't get a well-defined numeric value either. And this is understandable because remember, we're taking means here, and the mean of something with a true NA in it is going to be undefined. You can't know what the mean is unless you know what all the values are. You might have said something like mean x and NA dot remove equals true, and then we would have gotten a defined value. But we're not going to do that right now. We're going to go on and look at ways of signaling to the function caller special information about what's going on inside the functions. So just for recap, up here we're in section 9.1 we were learning about just how to invoke basic debugging in a function. The examples from section 9.9, I was showing you how to trap errors in your function arguments, where here we're actually checking x to make sure it's numeric, which it should be, and doing something special if not. Now, instead of just trapping errors, we're going to start communicating with our audience in fine detail and doing different things depending on what sort of things we discover about those arguments as we were examining them. Okay, so let me introduce 3 new functions in R that are sort of related. In the book I say it's kind of like the stoplight colors, red, yellow, and green, where red is something really bad, an error, yellow is just a warning, and green is just information for the user. The functions are message, which is sort of the green level, warning, which is yellow, and stop, which is red. Stop is the way we indicate that our function actually it's the way we generate an error inside a function. If the user gives us something which we really cannot handle, we can say, nope, that's an error, and in fact all the other errors you counter in R are probably generated with a mechanism very similar to this. If we see something that we think is strange, but it's not really illegal, we can just give the user a warning. Like we see some NAs and we're going to do something special with them. And if we just want to communicate something to the user and it's not really problematic, we're just giving feedback, we can simply issue a message. So message, warning, and stop are used in about the same way and about the same place, but for very different reasons, depending on what level of alert we want to send. So again, we're redefining the function called deviation. I'll define it first and then I'll tell you exactly what's going on. Excuse me. We're saying our function needs an x. And the first thing we do is say back to the user, okay, we're going to go ahead and calculate differences from a reference value, just communicating information. Now, we do our argument trapping. We say if any is NAX, we're checking to see if there are NAs in this vector, then we issue a warning because, you know, someone might glibly assume that all their values were good and maybe they're doing some other statistic which needs to know the number of values and they're going to report 8, but really it was only 7. So we're just going to give them a warning and say, hey, we removed the NAs for you. Well, that's just a warning if it occurs. Next we say if x is not numeric, exclamation point is numeric. If x is not numeric, then we should just stop right here because our function doesn't claim to know anything about calculating deviation from something that's not numeric. So we just give back some information to the user, x must be numeric, and let them worry about the solution. Then, if we got past all 3 message types there, we can go ahead and return the usual, where we take the mean, removing the NAs, as we hinted above, and subtract that result from the full vector of values. Of course, mean will be repeated once for each value in usual vector fashion, as we experience with R. So that's defined. Now we're going to pass in a vector of good values as I showed earlier with a true numeric NA rather than a character NA. And we can see our messaging starting to work here. Right away we see calculating differences from the reference value. Okay, that was our message. And then we get back the result. Of course, the NA element from our input data, you can't calculate a difference from that, so that just evaluates to NA. But the others all have a difference calculated from the mean of the remaining values. Nice. At the very end of that, we get the warning message. Now, you might have thought, hey, shouldn't the warning come before the result? Because if you look at the function body, the warning is actually encoded before you return any values. Well, yeah, actually, what R does by default is it stockpiles all the warnings and gives them at the very end. In case there's a great many of them, it assumes you would rather see the result first. There is a way to control that. We won't go into it right now, but you can force the warning to be issued right away if you so choose. Okay, well, that was fun and interesting. We don't know yet if our other line of code works. Actually, we saw the message, we saw the warning. If we want to see the stop, I guess we could change this back to character NA, and we should be able to encounter the stop message. And again, we see the simple inconsequential message, calculating differences. Then we see the error message. Error in deviation, yada, yada, yada. X must be numeric. Good. So we know at least that code is reachable. It functions as we expected to. And now we've said to the user, hey, it's your fault. You need to get the data correct. And then we'll do the right thing for deviation. In fact, the user is very often yourself. So it's a private conversation in some ways, but an effective one nonetheless. So we're going to switch that back the way it was and move on with somewhat of a more esoteric topic. That is the issue of branching. Because you see that in these examples we just read, we get, 2 or 3 messages of some sort or other all piled on top of each other, right? We got, say, the warning message and the regular message in at least one of those examples. It could be that you're thinking, that's far too verbose for my purposes. I just want my function to say one thing. If it's just a message, give me a message. If you really have a warning, then skip the message. If it's an error, just do that and don't go on with all that other stuff. Well, when your code does one thing or another, depending on some condition, the classic term for that is branching. So now we're talking about branching, and that's the section header in the book chapter. And we're going to discuss branching using this example. One more version of the function deviation. I've sourced it. It's being defined now as we wait for the very pokey network. I don't know what's going on out there. And let's just, before we execute anything, let's look what's happening inside. We say deviation is a function of x, yes, and then right away we say if x is not numeric, stop. In other words, we put the worst thing first. We want to trap that and say, hey, if we've got issues here, let's not even have a function. Let's just return to the user, give an error, and have them start over. Good, that's still going to be the only thing that happens. And the way we control that behavior is with the if syntax. It's a reserved word technically in R. It looks like a function, but it's not really a function. You do have to supply a condition, and the condition should be logical. It should be something that's either true or false. Just one value, a scalar true or false, something that evaluates to that. And you say if on that, and it does something. If that thing happens to be true, you get the coded result. If that thing happens to be false, you don't get the coded result. Now, like most languages, R pairs the if reserved word with an else reserved word. Using else immediately after if supplies behavior for the opposite condition. In this case, the opposite condition is that x is numeric. We're saying if not numeric, stop, otherwise, and then we have our option. We could do something explicit, or we could chain together another if statement. And you can do this if else, if else, if else thing all day and get all the conditions or all the cases considered that you want to. There are more formal ways of doing that in R. This is a simple one, so we'll just use if else twice. So here we have if, else, and then if, and another else. And our final else just has a regular old function call to evaluate. And we finish up the function with our usual return statement. So we start with our stop message, and if we survive that check, we go ahead and look to see if we need to issue any warnings. And if whether or not we survive that check, we go on and give a regular message. But this is interesting. We only give this message here if we didn't have to give a warning. Now that may not make logical sense the way these messages are expressed, but it does illustrate the fact that of the stop, warning, and message, only one of them is going to be issued for any given function call. Now, we're done with all our ifs analysis, and we get all the way down here to a regular line of code, the return value. This is going to happen regardless of the warnings and messages. You'll never get here if the stop condition was encountered, but assuming you got past that, then you just go on with the rest of the function body and it executes. For a demonstration, we try our traditional values. Deviation of 1, NA, 2, 3, 4, and 5. And in this case, we got the warning message, but not the stop message or the regular innocuous message. We change this, say, to a 3 or something and run that again. This time we should not get a warning or a stop. We should just get the calculating differences message, as we had hoped. That's a succinct illustration of branching using if and else. Don't confuse it with the function if else. I'll let you look that one up on your own. I've discussed it in the book chapter as well. It's very different from the reserved words if and else. Please don't confuse them. They have very different purposes. Branching is a classic topic in almost any program language. It has to do with flow control. The sibling to branching is looping, another classic topic for any programming language, and it also has to do with flow control. But now it's not about doing this or that, it's about doing one thing many times under slightly different conditions. So let's move on to sections or listings 9.16 and 9.17 in your book, and I've reproduced parts of them here. Maybe all of them, I don't remember. But they will give us a chance to illustrate looping and to discuss the various ways that you can achieve looping in R and why you might want to do one or the other. Okay, so the classic loop mechanism in R is, again, a reserved word, like if and else. The word for is also a reserved word, and it lets you iterate across a vector of values and do something once for each one of those. So here we're defining a function called numerics, and what this function does is it takes a data frame for x. I haven't shown that here, but that's what it's actually doing. And it assumes that x is a data frame. You could actually check for that using the error trapping techniques we just illustrated. And it takes a look at each column and tests whether those columns are numeric or not. And then it tells you something about them in the end. Okay, so let's step through it here. Well, first we'll define it. Pass it over to the prompt. And what we've done here is we've taken the number of columns in X and created a logical value out of it. So if you say something like this, n call of Theof, my favorite data set, it has 5 columns. So a logical of length 5 would look something like this. False, 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 all false by default. Okay, so that's what's going to be stored in this value over here called result. Now, we're checking in the next line of code, each value in a vector 1 to 5, or 1 to n call, whatever that is. And for each of those calls, we're going to call them call. Right? So first what's going to happen is call, the variable call, which we've defined on the fly here, is going to take on the value 1, and then it's going to take on the value 2, and then 3 and 4 and 5. And each time it takes on that new value, all the code in curly braces will be executed using that new value. So first we'll take the result vector and find the first element of it and replace that with the result of this expression, is numeric x call. So let's look at head of theof. You can see right away the head of theof, it looks not to be numeric. I think I remember that being an ordered factor. str for structure. Yes, subject is an ordered factor. I think that is not numeric. So this will evaluate here to false. That will take on the value false. And then names result. Here we're actually poking the column name into the name of the result, which is nice. And that gives us a way to index our results when we actually have them returned. So let's go ahead and see how this function performs on the table theof, the data frame theof. Well, I have the line of code right here. I'll just source it. We get back a vector of trues and falses that are associated with a name, a label. You see that subject is not numeric, but weight and dose and time and conc are numerics. That's nice to know because you can do different things with them depending what they are. Okay, so that illustrates the use of a for loop, where you just arbitrarily define some variable and use the reserved word in, and then pass in a list of values that that variable should take on. You can do exactly what you want using that variable and do it over and over and over again. The for loop is very easy to understand. I'll have to give you that. It also sometimes works better than alternatives because it gives you an explicit name for that value that is changing. That's very nice. The downside of a for loop is that it generally takes a lot of lines of code compared to alternatives. And also it runs slow. R is notorious for how slow the for loops run. So the good folks in the development world of R have given us a whole family of functions called the apply functions, which bypass the need for for loops. It's an alternative way to iterate, using a technical term. And the apply functions are much faster than for loops. They also take much less code to write. The downside is that they can be very difficult to understand, especially if the functions they perform are non-trivial. But they're fast and they're short, and I use them a lot. It's possible to overuse them if you get too hung up about converting everything from a for loop to an apply function. You might spend more time rewriting your code than you actually spend running it. And that's maybe not a good use of your time. But it's good to know how these work, and they're frequently handy. So all this mess that we did before as numerics, we can achieve the exact same thing with a single line of text, which I'll source now. We have redefined the function numerics to be a function of x, and all we're doing is we're calling sapply and passing in whatever x was. In this case, it's going to be a data frame. And sapply expects some object and the name of a function to execute on each element of that object. In this case, the elements of x are columns. So isNumeric will be invoked for each column in x. Now there won't be explicit names associated with that necessarily. We could get lucky in this case. But at least the apply will occur in order. So whatever you get back, you can know it's in the same order as your original object. You almost have to know that, otherwise there'd be no way to associate the results with the correct piece. So let's go ahead and repeat our function call, numerics, theof, and we see that we get exactly the same result back. sapply is really quite smart, and it passed along these labels as well. There's also an lapply and some other variants which you can check out on your own. But just note the difference. We've achieved the exact same thing, this time used the much faster apply version than rather than using the slower but more explicit for version. Feel free to ask a question about that if it went a little fast. In general, you should prefer the apply functions, and they will stand you in good stead in most cases. I have some advanced comments to make about these for loops. I think I'm not going to do that now in the interest of time. I may bring them up later if we have some extra time, either today or in the next section, next lecture. What I would like to describe for you now is a couple of issues concerning visibility in writing functions. And we'll do that with some illustrative code that I grabbed from listings 19 and 20 in this chapter. We are going to create a function called dfNames. And df here stands for data frame. Again, the data frame we're going to be using is the same one we used for the for loop, theof data frame, and you know what the names are. That's no surprise. I'm going to go ahead and write my function. I'm going to say, okay, I'm going to get a data frame, and for each name in the names of that data frame, I'm just going to go ahead and report the name. So I should see a bunch of names appearing on the screen, right? I'll go ahead and source that line of code. And there seems to have been no error with it. So now we'll go ahead and invoke that function with theof as the object. We have our return prompt, and I saw absolutely no output for that function. Well, this turns out to be a systematic issue in R. If you type something like 5 plus 2 on the command line, that's just an expression. R will go ahead and evaluate it. But since you haven't told R what to do with that, it's going to automatically print the result of the evaluation. Now, automatic printing is a structural component of R. They didn't have to make the language do that, but they did, because in most cases that's what you want to happen. The authors, however, figured or guessed that if you were inside a function or a loop, you probably don't want that to happen by default, because it'll happen so many times it'll be confusing and messy and all that. So to make a long story short, automatic printing is turned off inside of for loops and inside of function bodies. So to make this function work, we need to explicitly say print. We're going to say, yes, our language interpreter, we really did want to print this. Now we'll just say it by putting the function name there, and we'll redefine our dfNames function with explicit printing, and we'll try the same example once more. This time we get what we had hoped. we get a name being printed for each column. So what you see there is that we are promoting the visibility of something that happens inside a function. That's an important skill if you're writing functions that are supposed to report something to the user and you find that nothing's happening. You find that sometimes with plotting as well. If you're creating plots inside of a loop, you might, especially with lattice, you might just be creating those plots and you thought they were going to be stuffed in a file somewhere or come out in a default device somewhere, and you'll see nothing and wonder why. It turns out that inside a function body, you actually have to explicitly print those graphical objects rather than letting the system do that for you. So here we saw something kind of invisible that we wanted to make visible. Let's look at the opposite problem using listings 921 to 922. And here I've written sort of a weird function called unpack. It's not so important what it does here. I'll describe it anyway. We're really just trying to show the mess it creates on the command line when we run it. I'll define it first and then describe it. What this does is it takes something like a data frame and it calls lapply, one of our classic apply functions, and what that uses for arguments is the names of x. And for each name in x, we're going to write a function that grabs that name, we'll call it name, for lack of something more creative, and we're going to use the assign function to assign a variable with that same name in our global environment. Now the code's a little complicated. I don't expect you to memorize this all. Position 1 gives us our global environment. You can look at the help for assign later on. But what that says is, basically, if you come over here to the global environment, I see things like deviation and unpack and numerics, but I don't see anything like subject, weight, dose, or time. Now, after I run unpack on theof, then my goal here is that each of the columns in theof should also be objects in my global environment. Now, there may be reasons why you want to do that or not. That's immaterial. Right now, we're just doing it for illustrative purposes. So that's been defined. And let's just unpack, say, the first 2 records of theof. It's a very short data frame. Okay, so right away, I'll go back to my command prompt after having unpacked that and say ls. And now I see that subject, time, and dose, and conc, and all those are in fact objects in my global environment. I don't know what I want to do with those, but I can display them. Unfortunately, they were also displayed for me by default up above, just by the virtue of the fact that I called the function. So I'm saying to myself, that's really ugly. I didn't want to see them there all printed out like that. I just wanted them to be objects in my environment. So I'm going to go back to my unpack function and do the reverse of what I did before. Instead of making something invisible apparent, I'm now going to take something apparent and make it invisible. And you can do that in R with the reserved function name invisible. And it does exactly what you'd expect. It just returns the result of something invisibly. Of course, every function must have a return value, but it does not have to be a visible one. So something returned invisibly by default does not print. I can do the same unpacking that I did before, and I get the same result as before, but this time I don't see all the noise on the command line. Questions or comments about that? Well, great. Now you see 2 ways of controlling visibility, either by promoting visibility or demoting visibility as your needs require. That brings us to our last topic for this chapter. I'm debating whether or not to open that topic now because we have limited time left. I think we have time. I'm going to go ahead and try it. You'll see in your copy of the book, I'll throw it up on screen real quick, that at the end of the chapter, there are just a few problems to try, and they're all interrelated. Here's these exercises in section 9-10. There's 6 of them, and they build on each other, so in the end you really are only needing to do one thing that gets bigger and greater all the time. So have a look at that before Friday and do as much of it as you can. Hopefully I'll get through enough of the final topic that you can complete all 6 of those on your own. If not, we'll take all the time we need to go over that on Friday. And on Friday also I'll answer any questions you have about this material or anything else we've covered so far in this book or course. The topic then of interest is object orientation. In the book chapter 9, I give a very formal overview of object orientation. Here in lecture, I'm going to give you a rather informal overview of it, so you may benefit from both approaches in combination. And the point is this, that sometimes what a function does should be very sensitive to what it's acting on. I'll give you a good example. Not all functions in R are object-oriented, but some of the common ones are, like print, for example. Print. What should print do? And you know, the authors of the language could have tried to imagine all the things you might want to print someday and written a huge print function that checks for every object type. Data frames, vectors, time series, etc. And done a bunch of if else, if else, if else inside their function body to control the behavior of this function for each of those. That's an almost impossible task. Instead, what they did was they wrote print to be a generic function. So I'm just typing, oops, I didn't want to do that. I just want to type the definition of print. And you see that all print consists of is a single line of code. It's called use method. Use method for the function print. And that's it. And in fact, you'll see the same thing for summary. There's lots of things you can summarize in R. And at the time this function was written, there's no way the authors could have known all the things you might want to summarize. So they just said, okay, we'll write it as an object-oriented, what do they call this? A generic. This is a generic function. It just uses a method, uses the summary method for whatever object type you might be working with. So what happens is anyone who invents a new object, like a data frame or a vector or a time series or something else we haven't thought of yet, also has an opportunity to write a method for that object. A summary method, a print method, depends on what function you're interested in. And you can actually display all those methods in R. For example, if we say methods. Here, method is a fancy word for a function that is specific to a type of object. What are the methods for print? Wow, there are a lot of them. Some are non-visible apparently, but there are print methods for dendrograms and for data frames and for connections and conditions and all kinds of things. That's not so surprising. So when you say print in R, the language will grab the argument that you're trying to print, figure out what its class is, and come over here to this list and try to find a function that matches. So if you try to print theof, R will figure out that theof is a data frame, and it'll come and call the print.dataframe method, and that way just the right thing will happen at the command prompt. The same is true of summary. There's lots of things you can summarize, and we can check the methods for them. Not so many as for print. There only seems to be about 27 here. But you can summarize dates or connections or AOVs or GLMs. Can you summarize data frames? I don't see data frame. Oh yes, you can summarize data frames as well. At least something special will happen for a data frame. If the thing you're working with or trying to summarize is not on this list, then R supplies summary.default as the method of interest. And oftentimes the default methods do something that's pretty generic, something that would work for most object types that you're likely to encounter. So you see that there are specific ways of printing a data frame. There are also specific ways of summarizing a data frame. We've shown that the methods function will give you a list of all those specific ways of doing things. Now, let's stand that question on its head and saying, instead of what are the things we can summarize, let's ask what are the things we can do to a data frame. In other words, what specific methods have been written just for data frames? We do that this way. We say, what are all the methods for the class data frame? And here we should see at least two familiar methods. We should see the summary.dataframe, which appeared on an earlier list. We should also see print.dataframe here somewhere. Yes, it's right over here. In addition to that, there are special ways of R-binding a data frame, special ways of splitting a data frame, or subsetting a data frame, or transforming a data frame. So all these functions, transform, unstack, stack, dim, all those functions are all generics that have specific methods for data frames and maybe for a bunch of other things as well. Now, that's a lot of material and went very fast, but it's worth reading through the material in the chapter and getting your head around what object orientation is all about. It's very powerful. This idea that what happens when a function is called can depend on what it's acting on gives a lot of flexibility to the language, and it comes in handy in many ways. So if you are the author of functions, you sometimes may want to take advantage of that phenomenon. We're going to do that now because there is a function for summarizing vectors, and we can do this over here. We're going to check the head of Theof again, and I'm going to show you that there's an easy way to summarize a vector of numbers, say concentration. By default, when you summarize something numeric, you get a non-parametric distribution, some non-parametric statistics about that vector, such as min and max and some quartiles and even the mean thrown in. Those are things you might normally want to know for a numeric. Notice that it's non-parametric in orientation, and so no assumptions are made about this thing. You might want to analyze this differently. You say, hey, I've got a numeric vector which is parametric, and so I want to go ahead and calculate mean and standard deviation and good things like that, and some confidence intervals or whatever else depends on the assumptions, say for a normal distribution or otherwise. And what we do then is we write a new method for the generic function summary. And we do it this way. We say summary.parametric. And then instead of supplying simply quartiles, we're going to supply a list as our return value, where we supply, say, the mean of x and the variance of x and the standard deviation of x, and even some confidence limits, or at least a prediction interval around x. And we can go ahead and arbitrarily invent our own function for this imaginary data type called parametric. So we did this before, summary of Theof. And just to remind ourselves that the class of Theof is numeric, we're going to change all that, and we're going to reassign the class of Theof to be parametric. Now, when we try to summarize Theof-Conc, instead of seeing the usual non-parametric summary, we get something a little more interesting for our purposes. Very powerful. In fact, if you leave concentration right in the context of the overall data set, you can summarize the whole data set in one pass, and you see that you'll get the usual non-parametric summaries for weight and dose and time, but you'll get the summary that you defined for concentration because you have redefined its class and you have written a summary method for that class. That brings us up to the top of the hour, and that completes our topics for this chapter. So I'll stay online just a minute or two to see if you have any trailing questions. Otherwise, please have a look at the exercises in the chapter, and we'll see you back here on Friday with your questions. Thanks. I see a question here. Can we write a single summary function for multiple variables? Yes, I'll say yes. The problem is, it depends on what you mean by multiple variables here. The summary function is going to have to be written for a specific class. So if you can bind those variables together and give them a new class name, then you can write your own summary function for that class. On the other hand, I see a follow-up to that. Here, say a concentration and a dose. Do you mean a joint summary of concentration and dose, like combine them in interesting ways or somehow? If they depend on each other, then they would have to be part of the same object. I suppose you could write a summary function that checks for characteristics of what it's dealing with, regardless of the common class, and does different things for different cases. That would be one way of thinking about it. Independently, you say. Write a single function, say, for class and dose. Well, is this what you mean? I mean, we can do this. Let's look at the, this is fun. Let's do sapply Theof class. We see that concentration is now parametric. We could say Theof, let's say class of Theof dose is also parametric. And now when we do summary of Theof, we get the parametric summaries for both dose and concentration. Is that what you were asking? Very good. Sure. So it all depends on the underlying class. Summarizing a data frame is interesting because what happens is each column in the data frame is taken in turn and summarized independently using whatever method is appropriate for that column. And then the results are all squished back together in some form and printed on the command prompt.